probably seen a scene like this in a movie. A speeding car or truck's about to hit someone. The person dives out of the way to avoid being hit. Or while watching football, a defensive back tries to chase down a ball carrier from across the field. Or in soccer, a goalie dives to save a penalty kick. Each of these situations has something in common. A person has to choose an angle or direction before pursuing or escaping. If I was in the way of the truck, my instinct would be to jump directly to the curb. But maybe my instinct is wrong. Maybe I should jump away from the vehicle a little, or maybe a lot. In this video, we will solve the truck evasion problem 3 ways, using junior high mathematics, pre-calculus concepts, and calculus. So let's take these situations, math them out, and see what we can learn. Before we dive in, it's helpful to know that all these situations can be thought of as the same problem mathematically. We can relate the goalkeeper and the defensive back problems to the truck problem. We can think of the ball carrier or soccer ball as the corner of the truck barreling toward or by the defensive back and goalie. First, let's look at how to solve this problem using just junior high level mathematics. Here's a diagram of the truck evasion situation. Let's call the person in the street Sarah, after my only daughter. Sarah's walking towards the curb when she notices a large truck coming towards her. Let's make some reasonable assumptions about distances. Let's say the part of Sarah furthest from the curb is 10 feet away from the curb, and the truck's 40 feet away from Sarah. To first analyze this problem, let's think about the question, what point on the curb should Sarah run to? We'll come back to what angle she takes later in the video, but if we focus on what point on the curb she runs to, we can use junior high mathematics. The shortest path for Sarah to get to the curb is this perpendicular path. But we're not trying to minimize the time it takes her to get to the curb. We're trying to maximize the time between Sarah getting to the curb and the truck getting to Sarah. Running towards the truck is obviously not a good choice. That increases her distance to the curb and decreases the truck's distance to her. So that'll be worse for Sarah. But perhaps running away from the truck a little might be safer for Sarah. Suppose instead of running perpendicular to the curb, she ran to a point 1 foot down the curb from perpendicular. This increases the truck's distance to Sarah, but also increases Sarah's distance to the curb. How much though? We can use the Pythagorean theorem to find out Sarah's distance. Her path is the hypotenuse of this right triangle with legs of length 10 and 1. So her new distance is the square root of 101, which is about 10.05 feet. Doing this forces the truck to move 1 foot more, and Sarah only has to move a small fraction of that, 0.05 feet more, or 1/20th of a foot. What if she aims for 2 feet down the curb, or 3 feet? Are these options better for Sarah than running just 1 foot down the curb? Well, that depends on the speeds of Sarah and the truck. Let's assume the truck is moving at 25 miles an hour. Let's say Sarah can move an average of speed of 8 miles an hour while she sprints to the curb. We'll convert these speeds from miles an hour to feet per second to match the units, which is feet, of our situation. This gives us speeds of 11.7 feet per second for Sarah and 36.7 feet per second for the truck. With assumptions about speeds, we can calculate how much time Sarah actually gains getting to the curb. Since rate times time equals distance, then the time equals distance divided by the rate. Using a spreadsheet, it can save us time making these calculations. From the spreadsheet, we find that the optimal place for Sarah to run to is somewhere between 3 and 4 feet down the curb. We'll estimate the optimal spot to be 3.5 feet. This is great. We now have enough information to save my daughter. And for this situation, this level of accuracy is good enough, because in reality, Sarah would be lucky if she could guess even within a foot of the optimal spot in such an intense moment. It might be easier though for Sarah to estimate an angle to take instead of a point on the curb. And the angle would be the same no matter how far away she is from the curb. The solution of 3.5 only works if she's exactly 10 feet away from the curb. A simple way to find the approximate optimal angle that Sarah takes is to use the measurements 10 and 35 in the problem to draw a right triangle with legs 10 units and 3.5 units. Now we can use a protractor to measure the angle. It's about 20 degrees, maybe a touch less. But it's not like you're going to pull out a protractor and measure 20 degrees before running away from the truck. How safe is it to err away from 20 degrees? Should you err for less than 20 degrees and go more directly to the curb, or more than 20 degrees to go further from the truck? Or does it even matter which side you err on? Let's move on to some pre-calculus concepts to answer this question. First, we need to develop a trig function that represents our scenario. To calculate the safety time earlier, we use the equation rate times time equals distance, and then we solve for time to get time is distance divided by rate. The safety time is the difference between the truck's time and Sarah's time. So the general form is truck's distance divided by truck speed minus Sarah's distance divided by Sarah's speed. But now that we're using angles, we'll calculate the distances from the initial angle x using trig functions. The distance down the curb can be calculated by 10 times tangent of x. We want to use tangent here because we know the length of the adjacent leg to this angle, and we want to know the length of the opposite side. Tangent or cotangent are the functions that give the ratios of these two sides. So we can write the truck's distance as 40 plus 10 times tangent of x. Sarah's distance, the hypotenuse of the triangle, can be written as 10 times secant of x, or if you're more comfortable with cosine, 10 divided by cosine of x. We use cosine or secant because they're ratios of the length of the adjacent leg, which we know, and the hypotenuse. We can now write an expression that gives us the safety time in terms of the angle Sarah takes to the curb. So now we have a single function we can graph to easily analyze the situation. Here's the graph. Remember, we're trying to find the angle that maximizes the safety time. That means we're looking for a maximum on this curve. This point here tells us that the optimal angle for Sarah is about 18.6 degrees, and that gives her a safety time of about 2.8 seconds. Very close to what we measured by hand earlier. If she headed perpendicular to the curb, she would have about 2.4 seconds of safety time. So the optimal angle saves her less than 0.05 seconds. Is it safer for Sarah to err heading at a larger angle or a smaller angle? We can also use this graph to answer this question. Since the curve's pretty symmetric around the optimal angle, it doesn't make much difference whether she errs by heading at a smaller angle, which is closer to perpendicular, or at a larger angle. Although if I were in this situation, I would err on the side of taking a larger angle, giving the driver more time to slow down or swerve. This is what saves one of the pedestrians in the video you saw earlier. In fact, if we trace the curve from the maximum value over to this level, that is the same amount of safety time as going directly to the curb. That angle is about 35 degrees. Sarah could head in that direction, have the same amount of safety time, but it gives the driver even more time to slow down and swerve. How much more? About 0.2 seconds. Minimum, because if the driver does slow down or swerve, it can buy even more time for Sarah. What about the distance between Sarah and the truck? And the speeds of Sarah and the truck? Do these quantities affect the optimal angle Sarah should take? To answer these questions, we're going to move on to our calculus analysis. We can test this by changing the value of the distance in our function. But it is difficult to pick out a pattern using this approach. Since we're now analyzing the rates at which these quantities are changing, we want to use the derivative to further analyze these questions. Using the derivation techniques taught in calculus, we can find the derivative of our function. We'll call the derivative function t prime. To find the angle that gives the maximum safety time, we set the derivative equal to 0 and solve for x. With specific numbers, we could graph this function and find where it crosses 0. Without the numbers, we need to solve algebraically instead. That may seem like a disadvantage at first, but this process helps us to learn a lot about the situation and can result in a formula for the optimal angle that we can apply in other situations. Already, we can notice that the derivative of the function does not depend on the distance between the truck and the pedestrian. That parameter doesn't show up in the derivative, so it can't affect the optimal angle. As we solve, notice that the distance from the pedestrian to the curb divides out, so the parameter also doesn't affect the optimal angle. We learned this earlier in the video, but had to just try changing values in the function to see how they would affect the graph. Finally, we end up with a simple formula for the optimal angle. X equals the arcsine of the pedestrian speed divided by the speed of the truck. Turns out only the speeds determine the optimal angle, but it is even easier than that. Only the ratio of the speeds matter, or the relative speeds matter. If the pedestrian speed is half the truck speed, it doesn't matter what the actual speeds are. The optimal angle would be the same in those situations. I want to stop here for a moment and point out a few advantages that using a general model with parameters has over using one with specific values. First, there's no computation. Instead, we use the power of algebra in our analysis. Second, we can see how each parameter affects the solution. As some of the parameters disappeared through the process, we knew they didn't affect the optimal angle. The ones that are still in make it easier for us to understand the solution. Third, we now have a general formula for the optimal angle that we can apply to other situations without rehashing the work we did in the last video. Let's get back to our expression for the optimal angle. We can simplify the formula even further by replacing the ratio with one parameter or variable. We can call it x equals arcsine of r. This is extremely helpful in understanding these escape or intercept situations. What does it mean if r is greater than 1? Then the pedestrian is faster than the truck, and the pedestrian can just run away from the truck and take their time getting to the curb. It's not realistic or interesting. In fact, the model does not give an optimal angle for this situation since the sign ratios are between 1 and a -1. But what if r is less than 1? Then the pedestrian is going slower than the truck, and the optimal angle gets closer and closer to being a direct path to the curb as r approaches 0. That means in a situation when the truck is much faster than the pedestrian, the optimal solution is to basically head directly to the curb. Let's apply this a little to our other situations. This means in soccer, if the penalty kick is hard, so it's traveling much faster than the goalkeeper, then jumping a little away from the goal line to attack the path of the ball perpendicularly is better. It still might not be enough. If the goalkeeper's too slow, they won't be able to get to the ball in time. But so far, the model predicts that that's the best chance they have. We'll see if this holds up with further analysis in a later video. The football situation is different than the pedestrian situation, though, in two ways. First, the defensive back and the ball carrier are roughly the same speed. If they're exactly the same, then the value of r is 1, and the optimal angle is 90 degrees. That means the defensive back should run directly down the field and not toward the ball carrier at all. Well, that's optimal because we picked the best angle to maximize the safety time, and running directly down the field basically keeps that time at infinity. We don't have exhaustion or end zones in our current mathematical model. This brings up the other way that the defensive back situation is different. The defensive back is trying to get hit by the truck, just the far corner of the truck. So the defensive back's not trying to maximize the time. They're trying to take an angle where the safety time is essentially 0. This will call for a different analysis of our model, which we'll do in a later video linked below. Alright, as a quick summary, what we did in this video is we wrote down a general model with parameters representing the initial conditions of the situation. We took the derivative of our safety time function to find the angle that maximized the safety time. We found a formula for the optimal angle. The optimal angle only depends on the relative speeds in the situation, and we used what we learned to start to make sense of the soccer and the football situations. We also saw some of the advantages of using a general model, rather than one with specific values. The general model made it easier to understand how the different quantities in the situation, the distances and speeds, impacted the optimal angle, and it made it easier to find a general formula to apply to other situations. What's your favorite math problem? Share it with us in the comments. It doesn't have to be a modeling or real-world problem. Thank you for watching. Please subscribe and share our videos. Be sure to follow Math the World on Twitter, Instagram, and Facebook. Thank you so much for your support.